As a result of the above procedure, we have two classifiers. The first initial classifier, which was trained on all the training samples, and the second classifier, which was trained after the data has been cleaned with the first classifier, both using logistic regression using exactly the same procedure. And now we can use the two classifiers, to test on the intersection of the two data sets, where we are not sure whether the patients have type 1 or type 2 diabetes. And we can see here that before and after training, the classifiers indeed could tell that they are actually positive and negative samples clearly. Now we can draw a line where the two classifiers agree with each other, leaving a portion of the data which is uncertain to be manually verified by the clinicians. There is recall that the region with low posterior probabilities are type 2 diabetes, regions with high posterior probabilities are type 1 diabetes, and hence anything in the middle could be verified. Now the net effect is that if the clinicians need to clean the data, they need to only look at the portion of the data where the classifier is not confident. Now let's examine ourselves what we have done so far. On the left-hand side, initially clinicians would use a data dictionary to identify clinical codes. On the right-hand side, we just propose a data-driven approach where we use data to train a model, and we use the model to help us to identify clinical codes. Would the two codes agree with each other? The answer is yes, sometimes they agree with each other, but most of the time we get an explosion, in the sense that a big conflict. The codes found by the medical records may not necessarily correspond to doctors' expectations. And so this is a dilemma that needs to be resolved. How do we resolve these two codes sometimes? It is an ongoing research issues. Recall that we have two models, the model before cleaning and the model after cleaning. Here we want to see whether the clinical codes return make sense or not. Let's have a look. Now these clinical codes show that these are drugs. The drugs returned are in fact insulin drugs with subcutaneous injection. So patients with type 1 diabetes are likely to have insulin injected into their body because the body cannot produce insulin. The coefficients are positive, as you can see. So the patients with these codes would suggest type 1 diabetes. We have a diabetic on oral treatment. Again, that coefficient is negative, so it implies that if a patient takes diabetic drugs on oral treatment, he is likely to be a type 2 diabetes patient, because this is oral anti-diabetic drugs. So that's type 2, and the coefficient is negative. Third, we see that some coefficients here are positive, and we see that these are blindness. It says seen by optometrists, diabetic melacopathy, and these are typically symptoms, uh, common symptoms with diabetes, apparently suggesting that blindness is a leading complication of diabetes, likely to happen to patients with type 1. Now, whether this is the case or not, it is still an subject to investigate. There is also statin. So, prescribing statin can reduce rates of cardiovascular disease, apparently in people with diabetes. So, according to some study. And so the coefficients is slightly uh, favorable to type 1 diabetes, but again, this needs to be investigated. Now, we also have metformin. Now, metformin is a drug that attempts to dilute. Uh, uh, it's a drug that is commonly prescribed for type 2 diabetes patients. So the coefficient is negative. That makes sense. Now, of course, there are some other variables such as ethnicity variables. In this case, we see that uh, their coefficients is negative here. So if you speak the language of Urdu, apparently you are likely to be a type 2 diabetes patient. Uh, of course, the model, this doesn't say that if you speak Urdu, you're going to get type 2 diabetes. But people with type 2 diabetes, people who speak Urdu from the south of India, they're likely to contract type 2 diabetes. So there is some reasoning here, and this is found automatically by the model. Data-driven cause finding could be an important application of big data in healthcare. It can be solved by machine learning algorithms. It can potentially help clinicians to identify causes better. However, this still needs to be investigated further. In general, we need to reconcile between the domain knowledge, the existing domain knowledge uh, published in the literature with the knowledge extracted from the data. So if you can find a way to reconcile the two sources of knowledge into a uniform, coherent one, then the method could potentially be used more widely. And this is a ongoing research issue. So here is the conclusions of our talk. Healthcare is a big data problem. It requires not only hardware upgrade, but also software upgrade, including algorithms and workflow redesign. Our ultimate goal is to enable clinicians to carry their work more efficiently and effectively, and we do so in two ways. First, we help them to analyze data for service evaluation and for other investigative work. And second, we can help them to build better clinical decision support tool. Now, among all these aspects, when we deal with any big data problem, usability is a big issue. We need to create a tool that they can easily learn and use without too much effort.